If you remember, we had this Shephard lemma for utility optimization as well. In the case of utility optimization, we had one way to optimize our utility or to go to the optimal level of our goods and services bundle, which was expenditure minimization. Expenditure minimization. If you remember, in the expenditure minimization process, if we take the partial derivative of our cost function, expenditure function, the partial derivative of our expenditure function with respect to the price of a particular good, it would lead us to the Hessian demon function as a function of P and U. So we have the similar Shephard lemma for the cost. So now we don't have P, instead we have W. We don't have U, instead we have Y. Then if we take the partial derivative of cost function with respect to W, it will lead us to the conditional demon function. So if we take the partial derivative of this cost function with respect to W1, as a result will be Z1 as a function of W and Y. And when we take the partial derivative of this cost function with respect to W2, it will lead us to the optimal demon level for the second output. If you have as many output, just take the partial derivative of cost function with respect to that input price. If you find out the optimal level of X1, then just take the partial derivative of cost function with respect to the price of X1, which is W1. And when we want to find out the demon function for the X2, the optimal demon for the X2, then take the partial derivative of cost function with respect to the price of this input 2. It also comes from the envelope theorem, as we already talked before. So what does envelope theorem say to us? When we take the partial derivative of a Lagrangian function with respect to W, for example, some WL, it is equal to the partial derivative of this cost function with respect to that WL. As a result, we will move to some X star, for example, XL star, which such that this XL is a function of some Y and W. And finally, we will have XL, or in this term, we can simply, to differentiate, they can write down as a ZL as a function of W and Y. This is the envelope theorem. So by using envelope theorem, when we take the partial derivative of cost function with respect to input price, it will give us the conditional demon function, which is this one and also this one. And also another thing that we can prove from the envelope theorem is this one, the marginal cost value. From the cost minimization process, we have a lambda. If you remember in Lagrangian, we have that lambda. That lambda is equal to our marginal cost value. How we can find out that lambda is equal to marginal cost? Again, by using the envelope theorem, we can find out that lambda is equal to our marginal cost. So here, if we take the partial derivative of lambda now with respect to our output. The partial derivative of, let me write down somewhere to have more space. If we take the partial derivative of Lagrangian with respect to our output level, it will give us, or it is equal to, the partial derivative of our cost function with respect to y. With respect to y. And we have the Lagrangian like this, which Lagrangian is equal to wx minus plus lambda multiplied by f of x y minus f of x. This is our Lagrangian function, yeah? Lagrange is equal to wx plus lambda multiplied by y minus f of x. So now, if we take the partial derivative of this one with respect to y, then we will have, suppose when we take the partial derivative of this Lagrangian with respect to y, here we don't have y, here we don't have y, only have here one y. So then if we take the partial derivative of this y, which is equal to, this one is equal to lambda y, if we take the partial derivative of this one, the result will be what? Lambda. So then the partial derivative of that Lagrangian, so we know that. So now this partial derivative of cos is equal to this Lagrangian. Yeah? So instead of this one, just do this one. So take the partial derivative of Lagrangian with respect to output. When we take the partial derivative of this Lagrangian with respect to output, we will only remain with this lambda term. With this lambda term. So finally, the partial derivative of this Lagrangian with respect to y is equal to lambda. And also we know that the partial derivative of Lagrangian with respect to y is equal to the partial derivative of cost with respect to y. So then this one is equal to the partial derivative of cost with respect to y. And we know that when we take the partial derivative of cost with respect to output, it will give us our marginal cost. It will give us our marginal cost. And finally, we will get this result, which is marginal cost is equal to our lambda, but this is a function of w and y, because we have w and y here. So simply, when we see the cost minimization process, in the cost minimization process, that lambda in this Lagrangian method is equal to our marginal cost. Lambda is equal to our marginal cost.